Can I start now?
Yep, go for
Hello. Hello, everyone. Welcome to week 2 of Introduction to Advanced Machine Learning webinar series. Thank you for joining. I'm Funke Olaleye. I'm a data analyst with Sound of Your Love in Kitchener, Ontario. I'll be leading today's session on clustering. I'm excited to introduce you all to some new concepts over the next 2 hours along with Aryan. But before we begin, here are some announcements I'd like to make.
Hey, Funke, sorry to interrupt. Can you share your screen, please? You haven't shared it yet.
Oh, I thought it was sharing. Okay, let's escape. Oh, got it?
Yep, that's perfect. If you can present the PPT now, we would be set.
Okay.
Amazing. Thank you.
All right. Hello, everyone. Welcome to week 2 of the Introduction to Advanced Machine Learning webinar series. Thank you for joining. I am Funke Olaleye. I am a data analyst with Sound of Your Love in Kitchener, Ontario. I'll be leading today's session on clustering. I'm excited to introduce you to some new concepts over the next 2 hours along with Aryan. But before we begin, here are some announcements I'd like to make. First and foremost, a huge shout out to our amazing team of volunteers for putting together this series. We couldn't have this series without them. All of them are present as panelists on this webinar. For this session, Aryan and I will be the speaker, and all the other leaders will present on the chat to support you. Feel free to reach out to us with any question you have. Secondly, we would like to thank our sponsor, Home Depot, for putting together a much needed event for our community. Do show your appreciation for them by retweeting our posts. Elena will be sharing them on the chat. We're in the week 2 of the series, and here's what we have installed for the upcoming sessions. It's a single registration link for all these sessions. So if you're on this webinar, you are all set and you have registered for all the sessions. A round of housekeeping before we kickstart today's session. You can download the slide for today's session at this URL. One of our panelists will share this information in the chat. Feel free to download this and follow along. If you have any question regarding today's section, post them in the Q&A so that one of our experienced panelists can answer them during the session. If you are facing any issue during this webinar, do chat directly with the panelists so one of us can help you out. Finally, don't forget to follow us on LinkedIn and join our Slack channel. One of our panelists will share this information in the chat. Today, I'll be speaking about the concept of clustering. In the first half of the session, this is what you will be learning about. First, I'll start with an overview of what clustering is, why we need clustering, the difference between clustering and classification. I'll take an example of clustering from K-Means. I will look at some applications of clustering and its uses. I will discuss some types of clustering briefly. Thereafter, I'll drill down into K-Means clustering details for us to understand how K-Means clustering work with demonstration. I'll also discuss the challenges of K-Means clustering and its limitations. In the second half of the session, Aryan will walk you through the code implementation of K-means clustering on Google Colab. And finally, we will wrap up the discussion with a next step of additional reading and some new data sets you can try out with these newly learned skills. Yeah, before diving into the question of what clustering is, let's take a quick overview of our previous session. In our previous section, we explored supervised machine learning clustering, supervised machine learning algorithm and technique to develop models where the data had labels that are previously known. In other words, the data had some target variable with specific values that we can use to train our model. Most times, the input data will not come with predefined label or target variables. So we will need to develop a machine learning model that can classify this data by finding some commonality in the future by themselves, which will be used to predict the classes predict the classes on new data. This technique is known as unsupervised machine learning method. So, what is clustering? Clustering is a type of unsupervised machine learning method. Clustering can be defined as a process of organizing objects into groups whose members are similar in some way. Clustering determines the intrinsic grouping or natural grouping among the unlabeled data. The algorithm makes some assumption about data points to constitute their similarities. In other words, some characteristics that make them to be part of a group. Each assumption or hypothesis is made different but equally valid cluster. So we can also look at it in another way by saying that clustering aims at dividing the population or unlabeled data point into different groups and clusters, such that members of the same cluster are as similar as possible, while members of different clusters are dissimilar as possible. So in essence, clustering is a collection of objects based on their similarities and dissimilarities between the objects. Now, why do we need clustering? Let's assume you're given a data set you don't know anything about. Clustering algorithm can discover groups of objects where the average distance between the members of each cluster are closer than 2 members of other clusters. It is also worth noting here that there are no criteria for good clustering. It all depends on the user, the data, the criteria they use to satisfy their need. In this diagram, we can observe that members of data point marked red in cluster 1 are more closer than to members of data points in cluster 2 or 3. Likewise, members of data point marked blue in cluster 3 are more closer than to members of data points in cluster 1 or 2. You may be wondering, so what is the difference between classification and clustering? Let's start with classification. Classification is a result of supervised learning in which there is a known label that you want the system to generate. We often think about how to use data to make prediction on new data points. For example, if you build a fruit classifier, we'll say this is an orange, this is an apple, based on you showing the system examples of the apples and oranges, like we see in the diagram here. However, in the case of clustering, it is the result of unsupervised learning, which means that you've shown the system a lot of examples without labels. In this case, clustering might return fruits with soft skin, a lot of dimples, fruits with shiny, hard skin, an elongated yellow fruit, based on showing lots of fruit to the system without identifying the names of the different fruits. Next, let's take an example of clustering. Here is a problem statement. A cake company wants to open a chain of stores across a city and wants to find the optimal store location to maximize their revenue. What do you think would be the possible challenge? The issue here is that if they open many stores too close to each other, they will not make a profit. But if the stores are too far apart, they will not have enough sales coverage. First, they need to analyze the area from where the cake is being ordered frequently. Next, they need to understand how many stores to open to cover customers or buyers in the area. And finally, they need to figure out the location of the stores within all these areas in order to keep the distance between the store and the buyers minimum. The cake company already have addresses of their customer or buyers in their database. So they might as well use the information and perform K-means clustering to find an optimal store location. Okay, before getting into this map, let me walk you through a process of K-means clustering algorithm. The intuition behind the algorithm is actually pretty straightforward. To begin, we choose a value for K, which is the number of clusters, and randomly choose an initial centroid. That's the center coordinates for each cluster. We then apply a two-step process. Assignment step, which assigns each observation to its nearest center. And secondly, the update step, which updates the centroid as being the center of their respective observation. We repeat these two steps over and over until there are no further change in the cluster. At this point, the algorithm has converged and we may retrieve our final clustering. So for this map, here the company needs to specify the desired number of stores or clusters they want. Let's just say it's 3. K equals 3. So the customer or buyer at the black the black dots or spots, and the store are the stars, the red, the blue, and the yellow in step 1. So for step 1, we initialize the cake store randomly. We randomly position the stores, the red star, the blue star, the yellow star, to initially start the process. And in step 2, we assign each customer or buyer to the nearest cake store. The algorithm goes through each of the data points or dots And depending on what cluster is closer, it assigns the data points to one of the cluster centroid. Notice in step 2 that the color of the dots changes from black to the color of the store that they are nearest to. And here in step 3, we update the store location. So it does that by calculating the average of all the points in a cluster and move the store location to that average location. Thereafter, it repeats step 2 and 3 until convergence. So this step is repeated until there is no change or no movement of the store location. If you don't understand it, I can go over it. Otherwise, don't worry. As we take more examples, it gets clearer. So, application of clustering. Let's take a look at how clustering is being used. Clustering analysis is broadly used in many applications, such as market research, market pattern recognition, data analysis, and image processing. So let's start with customer segmentation. In today's competitive world, it's crucial to understand customers' behavior and categorize customers based on their demography and buying behavior. This is critical aspect of customer segmentation that allow marketers to better tailor their marketing efforts to various audience subsets in terms of promotional, marketing, and product development strategies. Some of the segmentation variables could be, for example, the number of items bought on sale, or average transaction value, or the total number of transactions. Another application is in creating newsfeed to cluster articles by their similarities or grouping tweets based on their content. Cloud computing environments use clustered storage to increase performance, capacity, or reliability. Clustering distributes workload to each server, manages the transfer of workload between servers, and provide access to all files from any server regardless of the physical location of the data. For environmental risks, clustering can be used to analyze environment risks in the area, like environmental risk zoning of a chemical industrial area. Clustering is also used in pattern recognition in images, for example, to automatically detect infected fruits, or segmentation of blood cells for leukemia detection. Clustering can also be used for trend detection in dynamic data by making various clusters of similar trends. In social networking analysis, clustering groups objects or nodes into classes based on their links as well as their attributes. For example, intuitively grouping individuals with dense friendship pattern internally, as we can see from the diagram here, and sparse friendship patterns externally. In biological data analysis, it can be used to derive plant and animal taxonomies, categorize genes with similar functionalities, and gain insight into structures inherent to population. Also, clustering can also be used in outlier detection applications, such as detection of credit card fraud. This takes us to the types of clustering. There are different types of clustering, but the most common clustering algorithm and the ones that we will explore today are the K-means, hierarchical clustering, density-based scan clustering, and Gaussian clustering model. So our first example of clustering is K-means algorithm. It's a distance, centroid, or prototype base. So K-means is an unsupervised clustering algorithm designed to partition unlabeled data into a certain number of distinct groupings. Let's call it K. The algorithm aims to find and group in classes the data points that have high similarity between them. Similarity is measured in terms of distance between data points. The closer the data points are, the more similar and more likely to belong to the same cluster. Another type of clustering is the hierarchical clustering. From its name, it builds hierarchy of clusters. It uses tree-like structure. It is an alternative to prototype-based, the centroid-based clustering algorithm. The main advantage of it is that we do not need to specify the number of clusters like we did for K-means. It will find the number of clusters by itself. It starts by treating each objective as separate cluster. Then it repeatedly executes the following two steps. First, identify the two clusters that are closer together. And second, merge the two most similar clusters. This iterative process continues until the clusters are merged together. The output of the clustering can be plotted using dendrogram. Dendrogram are visualization of binary hierarchical clustering. From the diagram below, we can see that A and B are closer. So they fuse together, and E and F are closer. So they also fuse together to form one cluster. And then we can see that the cluster between E and F are closer to D. So those two form another cluster, one lump cluster. And then the clustering between E, F, and D is now closer to C. And so those ones form another cluster. Eventually, this cluster is joined to the initial cluster A, and it forms one whole cluster. So the observation that fuses at the bottom are similar, while those that are at the top are quite different. The number of the cluster is based on the location of the vertical axis rather than the horizontal ones. So this clustering is further subdivided into two. You have the agglomerative and the divisive clustering. I'll start with the divisive clustering. Divisive clustering is a top-down approach. It begins with the whole set of a data points in one single cluster and proceeds to divide or split the cluster iteratively into smaller ones until each one of them contains only one sample. I might say a divisive clustering is rarely done in practice. That takes us to the second one, which is the agglomerative clustering. So this one is use a bottom-up approach. It begins with each sample as a different or separate cluster. So it merged them by the ones that are closer from each other. I mean, the two nearest cluster, until there is only one cluster, as we can see from the diagram. So to determine, so link criteria is a way of that determines from where distance is computed. If we use single linkage, then we start by assuming that each sample point is a cluster. It computes the distance between the most similar member for each pair of cluster and merge the two cluster with the smallest distance, like we can see here. And also there is also the complete linkage. It's actually the opposite of the single linkage. It compares the most dissimilar, the farthest data point of a pair of cluster to perform the merge. It uses the farthest data point to perform the merge. So pop quiz. Based on your understanding of hierarchical clustering so far, how many clusters do you think are in this dendrogram? Please enter your answer into the chat. Alenia says 4. Christiana says 16. Risa said top or bottom. There are many answers. Yes, I say it's 4. Yeah, you can say it's 4. I say, for me, I would say it's 4, but some might say 2. So I think the answer is 4. Thank you for your answers. It means that you're following along. So that takes us to density-based spatial clustering of application with noise. The DBSCAN is another clustering algorithm that is specifically useful to correctly identify noise in data. Of course, it is a density-based algorithm. So given a set of points in a space, it groups points that are closely packed together. The assigning criteria is based on a number of points with a specific radius epsilon and a special label assigned to each data point. The criteria for assigning the special label is as follows. 1, a specific number of minimum neighbor points, mean point, where here we say it's 3 in this scenario, and a core point will be assigned if there is this number of minimum neighbor points that falls within the radius. And it also looks at the border point. The border point will fall within the radius epsilon of a core point, but will have less neighbor than the number of the minimum neighbors points. And every other point will be noise. Like you can see from the diagram here, here is a core point, and here are the border points, and can only have 2 neighbors. It's either it's this one or this one. And this neighbor point can also have only 2 neighbors. So they have, in total, they have 3 mean points here. So in essence, what we are saying is that DBSCAN algorithm follows this logic. It identifies the core points and make a group for each one, or for each connected group of core points if they satisfy the criteria to be core points. Again, it identifies and assigns border point to their respective core points. So there's the difference between DBSCAN and K-Means algorithm. So the diagram shows how DBSCAN and K-Means find patterns in the data set. As we can see here, the orange circle is in the middle, and the blue one is just around it. What K-Means looks like a spherical, it uses a spherical shape type of pattern search to identify the patterns. And I'll just go through the points here. So DB seems to be to correspond more to a human intuition of clustering rather than the distance from a central clustering point like K-Means. When you don't know the number of cluster hidden in the data set, and there is no way to visualize your data set, it is a good decision to use DBSCAN. Because DBSCAN does not require one to specify the number of clusters in the data prior, as opposed to K-Means. You can find arbitrary shapes cluster. You can even find clusters completely surrounded by a different cluster like what we see here. And DBSCAN produces a very number of clusters based on the input. And of course, it can handle noise and outliers. So all the outliers will be identified and marked without being identified as any cluster. On the other hand, K-Means needs a number of clusters to be defined, though it's much faster than DBSCAN. So that takes us to the fourth one, which is the Gaussian clustering model. It is a probabilistic model that assumes that all samples are generated from a mix of finite number of Gaussian distribution with unknown parameters. So it belongs to a group of soft clustering algorithms in which every data will belong to every cluster existing in the data set, but with different level of membership to each cluster. The membership is assigned as a probability of belonging to a certain cluster, ranging from 0 to 1. It is one of the most advanced clustering methods. It is the generalization of K-means clustering that includes information about covariance structure of the data, as well as the center of the latent Gaussian. In other words, it is defined by a mean, which corresponds to the center of the distribution, and a variance, which says how the distribution is spread out. Well, it is another topic on its own, and we won't be getting so deep into it. Yeah, so this takes us to K-means clustering. We'll go deeper into this one, and I hope you liked it. So, as I mentioned earlier, K-means is one of the simplest unsupervised learning algorithm. K in K-means identifies the number of clusters. Mean in K-means is the averaging of the data to find the centroid. So K-means runs iteratively to find the total, to find the local optimal. The algorithm follows a simple and easy way to group a given data set into a certain number of coherent subsets called clusters. The idea is to find K centers called clusters centroid, one of each cluster, hence the name K in K-means clustering. As I said initially, the K represents the number of clusters. So in seeing a new example, the algorithm reports the closest cluster to which the example belongs based on a distance measure such as the Euclidean distance. So there are two key concepts used in K-means clustering. One is the squared Euclidean distance, and second, the cluster inertia. The most commonly used distance in K-means is the squared Euclidean distance. Last week, Sneha did a very good job of explaining in details the different type of distance metrics used in KNN algorithm. If you have not seen it, please review last week's session for more detail. One of those metrics she mentioned is the Euclidean distance metric. So Euclidean distance metric is computed based on the length of a straight line drawn between 2 points. That is the shortest distance you can get. So it's fast. Euclidean squared distance metric uses the same equation as Euclidean distance metric, but does not take the square root. As a result, clustering with the Euclidean squared distance metric is much faster than clustering with the regular Euclidean distance. For example, the distance between 2 points x and y in an m dimension space will give this equation below. So the sum of the squared difference of the distance between xj and yj, where j is the jth dimension or the feature column of this sample point of x and y. Cluster inertia is a sum of squared error within the clustering contents. It is the square difference between each observation and its cluster's mean. It can be used as a measure of variation within a cluster. The sum of squared error is represented in the equation where mu j is the centroid of the cluster J, and where the within cluster sum of I and j, the within cluster sum of square of I and j is 1 if the sample xi is in the cluster J, or 0 if it's not. So K-means aim to minimize the cluster inertia factor, or what is also called the within cluster sum of square criterion. Okay, get to see yet another illustration, a demo of K-means. As I've mentioned, some of it might be a repetition. I know we've seen this. So now let's take a look at how this works. Again, we said we have the initialization step, and the second step is the cluster assignment, the update, and the third step is the update centroid. So it begins again like with the initialization step, and they randomly pick K example from the data set as initial centroid. The goal here is just to select the centroid mu from a set of for each set of K clusters. So step 2, another way to look at this is that all the data points that are closest to the centroid will create a cluster. So it does this by assigning each data set to its nearest center based on the Euclidean distance and the data points and every centroid. So a straight line is drawn between two centroids. Then a perpendicular bisector, which is like a boundary line, divides this line into two clusters. So the updates centroid step, here we'll have new clusters. And so these clusters need new centers. So a new, a central new value is going to be the mean of all the examples in a cluster. So it repeatedly, it repeats step 2 and 3 until the centroid stop moving. Or otherwise, we say the K-means algorithm has converged. So here is a pseudocode for K-means clustering. I'll go over it. It's just another way of looking at this. So it randomly chooses K example as initial centroid, while K is true or whatever we have assigned as K to be true. It creates this K cluster by assigning each example to the closest centroid. It computes the new centroid by averaging example in each cluster. And if the centroid don't change, then it breaks out of the loop. So the purpose of the, in the while statement here, the purpose of the break is that while loop will continue in an infinite loop. So that's the reason why you have a break there. So another thing that I place right below the pseudocode is just a simple step that we can use to understand how K-means work. So it's just a simple, like initialize a random centroid. It gets into a loop until a loop of assign step, update step, until there is a convergence, then it ends. So K-means is fast and efficient method because the complexity of one iteration is a product of K, N, and D, where K is the number of the cluster, N, the number of the examples, and D, the time of computing the Euclidean distance between 2 points. So here, let us consider another example for a better understanding. Assuming a social networking site wants to find groups or clusters of people with like interests and direct relevant ads to them. One way to approach the problem is through clustering, where the firm may use features like such as page like, post shared, place checked into to build a data set and run it through a clustering algorithm to identify the relevant groups. So one thing to note is that the data is unlabeled. So let's just look, let me walk you through the illustration to see how K-means work, okay? So this data set consists of 8 points. They're not real data, it's just randomly generated coordinates for illustration. So those 8 points are plotted as blue circles. And okay, I'll go to the next one before. So for the sake of the simplicity, only 8 points have been considered here. Out of those 8 points, 2 points that we draw the X. That means we now make this to be centered. There's a circle here. We just place a cross on it to say, okay, this is our initial center. So we place a cross here and we place a cross on one of those data sets. Just for illustration. So the first step here is to randomly select K clusters. Here we have 2. And so the cluster centroid will be the green cross and the yellow cross. And the circles, of course, are the data set that we have here. So one of the other data sets looks like it's missing, but it's there. It's just under the green cross and the blue cross. Green cross and the yellow cross. So step 2 here is that the cluster assignment step goes through each of the examples. I mean, each of the data points or coordinates like we have here. We have X and Y. Don't mix it up with a label data. It's just a coordinate, just to give an illustration. So it goes through each of these points, and let's take an example of coordinate 3 and 1.5, which we are seeing here. So it picks up the data set, and its distance is calculated for each of the centroid. Remember, we marked this as a centroid. This is also another centroid for the other cluster we want to create. So it calculates the distance. So the step assign a data point either green color or yellow based on the distance that based on the distance of that data point from the cluster. So here we see it's been assigned because from the last slide, the distance here seems to be the shortest. So it's assigned the green because it's now in the green cluster. So after calculating the distance, the point is assigned. So the closest cluster, it takes the closest cluster anyway. It takes the assignment of the closest cluster to it. Next, the cluster assignment is repeated for each data point in the data set. Here on the graph, the data points 9 and 8. We're considering another data point now. Initially, we did the one for 3 and 1.5. Now we're considering another data point. So here on the graph, the data point is closer to the yellow one. If we consider the distance, we could see that it's closer to the data point. It's closer to the yellow data point. So it will be assigned the yellow cluster. So as I said, it gets the yellow color. The color changes to yellow because it now belongs. So it's going to do this for all the data points. And then finally, each data point or example of the data set is assigned to its nearest data point. So the update section is the next one. That's the step 3. So update section step does the following. It computes new cluster centroid by taking an average of the data points assigned to each cluster centroid. It averages all the points color yellow and green. It gives the new value of the cluster centroid. Okay, from this graph, we could see that after each example of the data set is assigned to its nearest point, the next step is that it computes the cluster centroid. You can see that every one now has the next step is to compute the new centroid. So it computes the new centroid and new average. The average now is now a new centroid. So it positions the new centroid. This is the initial centroid we started with. And so the average gets this value. So it moves it, positions it to the new centroid. And the same thing applies to the yellow one. It was initially here, it moves it to this side. So it does that for repeatedly do this, and finally we'll have a cluster and a cluster centroid. So you can see that the final cluster centroid seems to be the center of each data set. Now we get to see another animation using a real-time and real-time animation of K-means. You can follow along. You can click on, if you have your slide downloaded, you can click on the hyperlink in the slide and it will take you to the site. But I'll demonstrate how K-means work with this real-time animation, and you can watch. So again, it starts like the initialization aspect of it. It's like here we're going to have like K, it will be equals to 4. It's already preset for this animation. We can't change it. So it has a centroid at a particular spot. And then step 2, it takes step 2, then all the data points that are closer to the centroid will be created. And then step 3, it's we now have a cluster, and the new centroid value is going to be the mean of the example cluster. And it will repeat that over and over until the centroid doesn't move. So if we remember the little process that I sent initially, you have an initialization step, and then you move into a step 2 of assigning a data point to a cluster, and then it moves into it takes the average of all the data in that cluster, and then it now moves the centroid to the the value of the average. So let's try this. So as we can see from the diagram here, it's already gone ahead of me. And so it moved, and it's still moving. It's doing the looping section here. And now it has converged because it's no longer moving because it has converged. I'm not sure if we could do this. Let me see if we could go back a little bit. Let me try it again. So it starts with the data points, 4 data points. We calculate the distances, and it assigns this to a particular cluster. And then it calculates the average, it moves, then calculates the average again, it moves, gets into a cluster, it moves, goes through the loop, and until it converges. So how do we find the value, a K value? So next, we want to look at finding and choosing the optimal value of K. As discussed earlier, the algorithm starts with a random initialization step. A random initialization might lead to the algorithm getting stuck to a local optimal. One way to improve our odds of getting up with better value for cluster centroid is to run K-means a multiple time and choose a set of value that leads to the minimum value of distortion cost function given by the equation here. So the cost function computes the average of the squared distance between each of the data points, xi, and the cluster to which it has been assigned, mu, the cluster that has been assigned. And the smallest value of the cost function corresponds to a better initialization. It's also known that this technique is effective for values of k that is less than or equal to 10. But it has been also observed that for the larger value of k, it does not make a significant difference. So for a larger value of k, the K-means algorithm will pretty much converge to acceptable values of the cluster centroid. So it is computationally expensive if you do that. So of course you want to get the optimal value of k. So another method we could use is the elbow method. The elbow method is used to determine the correct number of clusters in a data set. So it starts by plotting the ascending value of k against the total error, the distortion cost function, obtained when using that k. So it chooses a value of k where the graph elbows out or have a sharp turn. So you'll find the elbow where adding more cluster makes no longer improve the solution. Like what we say, you're adding, you have 3, and then you have 4. You can see that the cost function is not really changing that much. So the optimal value here would be 3 from the graph that we're seeing. I think there is a typo here. Yeah, okay. So let's look at this graph. Wow, look at that. We have a curve that does not fall within the guide of choosing a value k, where the graph elbows out or we have a sharp turn. So when real world data is plotted in this graph, as we'll see, it does not usually have that prominent elbow to pick a value k. So can anyone, what a question, can anyone tell the value of k from the graph? If you know it, can you please put it in the chat? Somebody says 7. It looks like 7, but then we say we have to continue to see that it's really decreasing. Well, it has already stopped at 8. Somebody says 7. Well, if it's still continuing, and we still have the graph going all the way down, then we could say, yeah, it's 7. To me, it might be 7, but sometimes it might not be 7 because you might still want to draw to have more clusters. Anyway, thank you for your answers. So let's try another one. Here are a few more diagrams using the elbow method to choose the cluster. So we have another pop question here. What is the optimum number of cluster in this diagram? let's try the first one, the top one. Sorry, I didn't have the label there. The first one, you can just say, this is the first one, A. The top ones will take A, B, C, or D, or you could say 1, 2, 3, and 4. So if you have any answer for any of them, just give the, say 1 is a cluster, it has 3 cluster. Just let me know what you think. So I see somebody says C, it's 6, and D, it's 5. I'm sure you can all see the response. Yeah. And Kedika, I think I'm pronouncing your name well, says 1, 2, 3, 4. No way to find it. I can tell. It's not easy to find the K value here. It's not so clear. So sometimes K means, I mean, using the elbow method might not give you what you really want. So I would say sometimes it's not as easy as the other. So some are easier than the other. For me, I cannot really pinpoint what the A1, the cluster for the diagram A. I can't really point this one because it's still descending. We can't say it's 17 here because it's still declining. It has to get to a stage that you don't see it declining that much. And here, it looks like, well, we could say 6. 6 looks to be okay for C. And for D, I'll pick somewhere 5 and 6. So sometimes you'll probably be guessing, oh, could it be 5 or could it be 6? So that's how the elbow method could result into. Sometimes you don't have a particular, no automatic way of picking the K value. So how do we do that? So the parameter K sometimes is manually picked from looking at the visualization. So that takes us to K-means limitation. So K-mean, of course, we say is a simple algorithm, but it does not, it's not without its drawback and challenges and limitation, as we can see here. We need to specify the number of clusters, but we don't know how many there are in. So it's subjective. I could say it's 5, and some could say 6, and all that goes around. So the result can also change depending on the location of the initial centroid. And the K-mean clustering analysis isn't recommended where you have a lot of categorical variable because it depends on numeric value to compute the distance. So in that case, the categorical variable will need to be converted to numeric. And also, K-means assumes that clusters are spherical, distinct, and approximately equal in size. Remember, we could see in the diagram for the DBSCAN and the K-means when we show the difference between them, we could see that it looks like it's always taking a spherical shape, that it looks like a spherical shape. So, so they're not very good to identify classes that when dealing with groups that do not have a spherical distribution. Like if you have something that's curving this way and the other one is curving behind it, it would just take a part of it. So you also have the trouble clustering data where clustering varying sizes in density. So centroid can be graphed by, the centroid can be dragged by outliers or outliers might get their own cluster instead of being ignored. So K-means algorithm doesn't necessarily converge to a global optimal, but instead may converge to a local optimal. K-means is not guaranteed to find the best solution. In fact, depending on which value we choose for initial centroid, we may obtain different results. In the diagram here, instead of having 3 distinct clusters, we'll look at the global cluster. I think I'm almost out of time, but I'll quickly wrap this up. The global one, you could see 3 distinct clusters here. But in the case of K-means converging to a local optimal, it will probably change the setting in the sense that it splits one cluster into 2, or it could combine 2 clusters into 1. That's another limitation of K-means. So to wrap up, let's just summarize what we've learned. We started with clustering, what clustering is, why we need clustering, the difference between clustering and classification. We looked at an example of clustering with K-means. We also talked about applications of clustering, the different type of clustering, the K-means, hierarchical. We also said it's divided into divisive and agglomerative. We also have the DBSCAN. We also looked at the Gaussian clustering model. Thereafter, we dive deep into K-means clustering to understand how K-means algorithm work, and in some demonstration, and also how to choose K-means. We concluded with the challenges of K-means, clustering and its limitation. So all right, we'll see that we are got to the end of the first half of this session. Thank you for staying on with me. In the next half of the session, Aryan will walk us through the code implementation of K-means. And if you have questions, please send them to the Q&A, and our panelists will answer the question. For the time, just for us to get a little break, we can take a 5-minute break, and Aryan will continue from here. Thank you so much.
Hey all, thank you, Funke, for teaching us the intuition behind clustering and the concept behind different clustering algorithms. Now that we all done learning the concept behind clustering, let us get our hands dirty with and try out some new real-time data, and that can be found in the link of the slide. You can go to this and just open the link, and one of our panelists will share a link in the chat. Kindly open a new tab and feel free to follow along with me. I will spend a couple of minutes to show how to open code from GitHub in Google Colab and create your own copy of this. Just go to the link and just copy the path. Just open and just upload. Just open the Google Colab and just open upload a notebook. Space the GitHub path in it. Now you can new tab. Just save it to your drive.
Hey Aryan, sorry to interrupt.
Yeah.
We're not able to see your Google Chrome screen. We're still on the PowerPoint.
Okay. Sorry for that.
And another thing, it seems like the audio is a little spotty. Can you try turning off your video? Usually that helps when you're sharing your screen.
Okay.
Thank you.
I think now must be visible. Go to the link and just copy the path above and just paste it in here. Let me show you again. Go to files and just upload a notebook. Go to GitHub and then paste the URL here. Just open it. Open it a new tab. And after opening, you just have to copy to your drive, and then you can be hands-on with this. Yeah. So let's we can get a quick recap from the clustering algorithm that you can access from the from this link, and what the clustering is. What is the K-means clustering means? The objective of K-means clustering is simple. It groups similar data points together and discover underlying pattern. To achieve this objective, K-means looks fixed number of K of clustered in data set. Basically is identify the centroid and then allocate every data point to the nearest cluster. The mean in K-means is just finding the averaging of data and basically the finding the centroids. So how it works? To set the cluster, set data point, the algorithm start by random initialization of centroid for K cluster, iteratively updating the position of the centroid to best split the data points. The cluster assignment, and basically there are two steps. The one is cluster assignment and second is centroid updation. So what we get from here, let me show you. So, first we do the cluster assignment. We first find randomly initialize the centroids. So we have initialized centroid here and one centroid here. And after initialization, we have just made a nearest point to the cluster and made a decision boundary in between. So after that, we have find the mean to all the data points. So we have find the mean all data point is lies here, and we then update the data center. And similarly, go to the red side, and we update the data center, and again we made a decision boundary in between. So we make decision boundary feel like this, as it shown here, and then we again find the nearest. Then we again uh, update the centroid by finding the mean of the data points, and it goes like this. It goes like this, and again we draw this boundary, and we do this iteration or this this again like again till we get the convergence point. What does convergence point mean here? It means basically the cluster. It means basically the before iteration and after iteration, the data centers are same. At the same position we are getting, and we are not getting the updation in the data center, so we reached to the convergence. So basically, what our goal is cluster quality. Uh, Our goal here is just not to make many cluster, but to make most meaningful cluster. We can measure the quality of cluster using a metric called inertia, and the inertia is the average distortion. So we want less distortion in our cluster, so we can get to the most out of the cluster. So distortion is calculated the sum of squared error, where error is considered as the distance of every data point from cluster centroids.
Hey Aryan, sorry to
Yes.
interrupt again. Quick question for all the members who are on this call. Can you tell us if the audio is good or not by giving us a thumbs up or thumbs down so that we can rectify it? We see quite a few thumbs down. So we just want to confirm if everyone can hear, or is there something we should rectify from our end? So please give us a sign on the chat so that we can rectify it and make this session useful for you all.
Now audio is clear. All
The audio seems pretty spotty from my end. So Aryan, can you try disconnecting your audio and reconnecting? I think that might help.
from now is audio clear now?
I think it's a little better now.
Okay.
Um,
Where should I start from?
so maybe we can skip the recap since Funke just covered that, and let's go on to the
Okay.
second section.
Okay. So I was telling just about cluster quality, and just let me complete the cluster quality, and just let me complete the elbow method. Okay. So what does the elbow method means? Elbow method basically K-means clustering of a data set from the range of the value of K. Basically, we are just calculating the K value, and we expect this produce a long tail. As we increase the clusters, the distortion will reduce. Our goal is to identify the elbow and optimize the cluster without overfitting. And we can get more information from the session at this link, and basically what is the implementation of the K-means algorithm. So we are using the make block function from sklearn to get a mimic of dataset, and our main goal of K-means clustering is to use the external ML package and to understand how it performed. Okay, so what we are doing is that we are we are just importing NumPy, Pandas, Matplotlib, and sklearn dataset in for the makeBlock function, and we are just having these. We have these colors in our list we are using, and this is number of cluster of centroid we are using. We are using 5 centroid, and we have 500 samples with 2 features, and K center K, and random state we are taking as 10, so we can initialize, and there are the 500 features, and uh, we have there are 500 samples and with 2 features each, and here we are making just a cluster dictionary. In that we are just making the cluster dictionary has some 3 points like centers, points, and colors. So every cluster should associated with a center, and each center associated with points, and each has a color. So we are just initializing a center randomly, and now we are just looping over all the cluster dictionary, and this is how we calculate the Euclidean distance. Earlier, you will know if you attended the first ML webinar, and they are how, and then we assign the points to cluster. Then distance, basically we are just finding the distance of k centroids, and we are just finding the centroids and using each center from each center of centroid from the cluster, and just appending the distance of the centroid, and based on the distance of k centroid, pick which cluster to assign to it. We are just using in the argmin here and to find the minimum distance of the cluster, and then we are appending in the cluster dictionary and then update the cluster centroid function. We here are just using the cluster points, and we are updating, and we are just convert, because the cluster point are in list, so we are just converting in array. So it will be in array of array, and we are, if the length of, if there is a point, if any cluster center is not associated with any of the points, so we don't want that cluster to be updated. So we are just ignoring that here, and then we are just plotting the cluster, its points, cluster color, cluster center, and this, and then the and after the plot, we have just doing the iterations, and we are getting this output. Oh, sorry, yes, there is a low load in dataset code. What are you asking about? No load in dataset. Okay, so here we are here what our initial data set was, and then we just calculated it. We just randomly initialize the data centers, and after that we have just find the nearest point to the data centers. So you can see that this is not allocated any points in the data set. It is data center not allocated with any data points, and after that we are just doing updation and taking the mean or average of the data points according to the data center allocated to it, and then after then we meet the stage. This is called convergence, and this is the final output. You can see it here. And then earlier we are doing just randomly initializing the data centers in the first, and then now, and then here we are using K-Means plus plus. So K-Means plus plus helps us in doing the initialization better than doing it randomly. And so we can see it here. We just have to make fit the data here and just provide the clusters we want. We're just providing the cluster 5, and just we are seeing what is the inertia. Inertia should be less, so we get the less distortion in the data set. And, and also here we are just getting all the iteration or to converge. We are getting the iteration and we get the convergence like this. There are some iterations we have done, and like assign point, plot cluster, update cluster, assign point, and update cluster. So after some iteration, we achieved the convergence. So it's telling about the iteration, and we get converge, and all the centroid. So we have provided the 5 clusters in initial step, and we are getting the five plus a centroid, and this is how we are getting it. And suppose if we don't provide any clusters to it, like if we are providing now 5 and we are not providing any clusters, so how we are getting it? So let's do that also. And if we are not providing with any, if we don't initialize the number of clusters, so it automatically or defaultly initialize the number of cluster with 8. You can see it here, it initializing the number of cluster 8, and we are getting 8 cluster. Accordingly, we get the 8 data centers and the points associated with 8, and you've got the 8 clusters in it. So you can go to this and you can go to this and yeah, you can go to this link and see all the parameters and the attributes associated with the K-means, uh, K-means echelon level. Yeah. So let's come to, so yeah. Thus, even though data visualization is more interesting, we have 5 cluster earlier, and now we have 8 cluster. Yeah, in this diagram we are seeing. Yeah. So now come to a problem: the more customer data set. You are a marketing business analyst at Malala, a premium mall in New York City, and you can use clustering to identify marketing strategies. Though a loyalty program, your company has collected some information on patterns such as age, gender, annual income. The team has also defined metric spending score based on the spend frequency history, basically the how the person spends, and the value ranges from 1 to 100, and higher this value, the more valuable the customer is to the company. Basically increasing the marketing strategies and building it, how we can increase the mall marketing, how we can increase the marketing of the mall and sales of the mall. Yeah. So you are assigned more tasks, understand the patterns. You have signed up a loyalty program, and yes, and identify the segment of customer. We have to identify which type of customer is more valuable and how to increase the sales basically according to our customers, and strategize and provide incentive to segment or certain customer which have the more spending score. Yeah. So you can get data set from Kaggle. So just go to the just go to this link and you can get on handy the data set. One of the panelists will give us the link in chats. And yeah, this is a data set and you can just download it. I have already downloaded it in my downloaded folder, and let me open the downloaded folder. Not opening. Yeah. Have downloaded already in my downloaded folder. You have just to upload it on the Jupyter, upload it on your Colab. You go to your Colab and just upload it here. You can from Kaggle dataset and just upload it here. Just I uploaded a dataset here, and then you can go and just copy the path from here. You can get the copy path from here and just paste it here, and now you can read the data. And now we are just have the age, annual income, and spending score. And since we are plotting the n-dimensional space, it is tougher to okay. And let's get from here first. Yeah. So what we are doing is that we are just yeah we have just uploaded data, and now we are using n-dimensional space to validate the this use case. There are the 3 numerical columns for the data set, and we have the features combining, and we find the optimal value of K using the elbow method and visualize the result from our K-means model. Based on the visualization, we attempt our marketing strategies and all. So we first access the data from the file we have uploaded here, and then we just use the elbow method. Basically, we are just calculating the inertia and we are just appending it in WCSS. It is the within cluster sum of squares, and we are just appending it. And now we are just ranging it from 1 to 21. Basically, we are basically it's from 1 to 21. We are just making the plot, and we are just appending the inertia we find from the K-means, and we are just making uh, we are just appending it in a WCSS in a list, and we are just plotting, and we we have found it that the optimal cluster we achieved from this method is 5, and we pick here from 5, and we try to build cluster, initialize the cluster 5, and using the initialization K-means plus plus. This we are using the K-means plus plus here initialization method, and we are just using fit predict, and it will predict all the coordinate points, and we are just initializing all the coordinate points, 0 axis 1, and we are just using the label low. Let me explain from the plot. So what we get from here is that we got the 5 type of customers. We got a 5 cluster basically, and what we get from here is that annual income and spending score. So this type of customers, as you can see, has the low income, low in, but high output. So they are spending more and they have no income. So we can provide them with some higher loyalty program to that type of customer, so they can increase our marketing of the mall. And also the annual income of this type of customer is high, and also they are spending more. And these are the some of the customers that have average. These are general type of customer that have average income, and they are spending also average. But these customer are these this type of customer are spending less on the spending less in the mall, or they are less buying or doing this. So we can develop business insight. We identify the 5 cluster as I told you, and we see high in low out. These customer income spent in the mall and aren't due to the variety of reasons, not aware of, not interested. So we can develop marketing strategy accordingly. And these customers are spending low in and high out. Basically, this customer, this type of customer, are spending more, and they have lower annual income, providing additional incentive to them so they can continue and be our valuable customer. Basically, I told you that providing some loyalty program to these type of customers. So we can easily visualize this data that is plotted 2D, plotted in 2D. Okay, so in this data, basically we are plotting annual income and spending score. Now we are using like age and spending score to visualize some other marketing strategies. So again, we are doing the same, and we are appending the inertia in the WCSS, and then we are plotting it from 1 to 21 using K-means plus plus, and then we are just got the finding the optimal value. So here, if we see clearly, we have 2.5 and 5. So if we take the average of that, it comes to be 3.75. And as we see, this point and is somewhat more towards the right hand side. So we can pick the value K as 4. So we are just picking it just clicking it like this only, and I have taken the average of this, and we have seen that it's towards the right hand side. That's why I'm taking the 4. And again, just plot using the K-Means plus at initial method to initialize the points, and just doing fit predict and just plotting all the points and the cluster centers we are getting. And then the business insight we are getting that we have 4 clusters, and we have 4 type of customer segments we have in based on the age and spending score. And we divided into some categories, like we have young customers that spend more on the mall, and we have 2 young customers that spend some less on the mall, and we have the older customer that spend average on the mall, and there are some older customer that spend and less on the mall. So what we initialize that the general population is this one, and the general population are of people who, regardless of age, have a low spending score with mall, and marketing strategies can be built for this group of age agnostically and older. And basically in older, yeah, the older population is mid-level spending score with a mall, and we can see that the older have mid-level of the spending score around 60 to 40, and here higher annual income than a younger population would be great target for marketing campaigns. So you need to ensure an inclusive of the older population and target ads towards them, increase spending score, and provide them with some loyalty programs. Yeah. So now we are doing is that we are visualizing between age, annual income, and spending score. So we are plotting a 3D graph, a 3D plot, and we are using all the 3 data set in it. And again, we are just using WCSS to append the inertia and calculating the 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 plot for the optimal k value, and how we pick the optimal k value. Okay, so uh, so you can see that this point this point is somewhat the the elbow. We are seeing it here. So we can, and it is also having the less number of inertia too. So we can take the average of 5 and 7.5, and it is around 6, it is around 6.25. So oh, so 6.25 is here, and and the uh, the elbow is somewhat around left. So we are taking 6 for our convenience and using it. And same, we are initializing with K-Means and we are just plotting all the points here, and we are just axis 0, 1, and 2, and with the colors, and S is the size, and this is a marker, and we are just using. So what we get from it, it seems to be some complex, and if we see the visual, and within each cluster of color, there is some different shades that denotes the point based on the graph. Since it's 3D, so it is as the plotting increases, 2D to 3D, the complexity also increases. So the higher dimensional clustering algorithm is tough to visualize and see. So we use 2D to visualize more better than 3D. So as the dimensions increases, the clustering algorithm complexity also increases. So yeah. So the outlook for the dataset is that you can try gender to analyze your customer, uh, and uh, and identify 5 target population dataset as we have told you, and you can get get more and more around the around the populations and make more better marketing strategies that we have told you. And also you try to analyze the gender to analyze the cluster of your customer. So let me again go to the slides. Yeah. So now that we saw how to implement K-means clustering on real-time dataset, here are some ways to improve and refine the skills we just learned. There are 3 homeworks points. Do attempt them all and share your result with us on Slack at the Learn ML channel. All the titles are URLs and you can use them and access the information you would need. And the first homework is look through the clustering documentation from sklearn, and we implemented one algorithm of many algorithm, and Funke taught us concept for and explore the algorithm and try implementing them on our notebook to see how the result differed from the K-means algorithm. And secondly, in the mall customer notebook that we have just saw, there are some homework section present. Try them out and let us know how it goes. Thirdly, we have some additional codes to share on using the clustering with images. In this notebook, we understand the kind of application of clustering with images. So you can go here and just click here and go to the link. My screen. Yeah. So you can do the clustering with images. It's a cool project, and into image compression. I have added some images here. Basically, what it doing? It just processing the image, and you can find out the what are the main thing we're getting from cluster. We are getting green color from the trees. From the sea, we are getting blue, light blue, and from here we are getting dark blue. So you can use in K-means here and use this this mini project. You can optimize optimum value of K, and also you can try out these things, increase the value of K to see how can we represent the least resolution and best quality version of the image. Try out different images. I have added some links here. You can try out these images and think of the ways to optimize the site K value interventions. Like you can make the classes for the K-means plus plus. Basically, you can try out these things, and after there are other applications, then compression, like you can do also that. And at last, uh, yeah. So you, I hope you enjoyed, and thank you for all joining today's session and taking off your weekend to learn new concept. If you have any questions regarding this content, do join us on Slack and post your questions to help me channel. And one of our panelists will give us the link there, link in the Slack, and we will look forward to seeing you all next week when Joseph and Rishika will covering the basic concept behind the outlier detection. And have a great rest of the weekend. And hope you liked this uh, webinar. Thank you. Sorry for the sound. I think I have tried, but there are some issues there. Thank you.